All right. So in the last chapter, when we were talking about probability, we were describing specific events, like heads or tails or rolls of the dice. In this case, we're going to be keeping track of variables and finding the probability of those variables. And so we're going to keep track of the variables that take on set amounts. And we're going to be focusing on discrete variables. So discrete variables, you've talked about this before when you talked about functions being discrete versus continuous. A discrete variable is going to be a collection of isolated points. In other words, they take on very specific values, and they can only be those specific values and nowhere else in between. Versus continuous variables, which are connected and can take on basically any value, including any fraction or decimal or anything like that. And so what I have down here is some variables and shown as discrete versus being shown as continuous. So for example, we can take a continuous variable and make it discrete, or a discrete variable and make it continuous. So we have something like foot length, how long your foot is, but we're not going to make shoes for every single possible length of foot that someone has. We take that continuous variable, which is your length, that could be any value, and turn them into discrete amounts of sizes. 8, 8.5, 9, 9.5, 10, 10.5, and so on. So that's taking a continuous variable and making it discrete. Or when we ask how old someone is, we're not usually asking about the continuous idea, which would be which between the start of this sentence and the end of this sentence, your age has changed. You are now older than you were 5 seconds ago. But when I ask how old are you, that's not what we're usually talking about, and you're not going to update me every second with how old you are. Right? You would say, like, I'm 16, I'm 17, I'm 72. And so we turn that into a discrete variable that we usually measure by how many birthdays we've had. Sometimes we use halves if we're young. But that's turning a continuous variable into a discrete. Another way you can say is like bus stops versus a cab ride. If you have a bus stop, if you're on a bus or a train, then they usually have specific stops, specific places that they pick people up and drop people off. And you can only get off or on at those places. That's discrete. Continuous would be something like a cab ride. You take a cab, and you can say, I want to go to this place, and they can take you there. Can take in any value. That's continuous. But we're going to spend most of the time talking about discrete variables. We've already talked about some continuous stuff, and we'll look at it again at the end of this section, but we're going to spend most of this chapter talking about discrete variables. And so most of the time, a probability distribution, which is something we've already looked at, as is a table that gives the value and the probability of it happening. So it lists out all the possibilities and lists out the probability of each of those possibilities happening. So let's say that we flip a coin 3 times. And we let our variable x be the number of times the coin comes up heads. So if I flip 3 coins, then you can list out all the different possibilities of coin flips we can get. We can get heads, heads, heads. We can get heads, tails, heads. We can get heads, tails, tails, and so on. There are 8 different ways that the 3 flips can happen. 2 for the first one, 2 for the second one, 2 for the third one. So 2 times 2 times 2. And so what makes it a discrete variable is that we're keeping track of how many heads do we get. So first we're going to list off the possibilities of the number of heads we could get. We could get 0 heads, we could get 1 head, we could get 2 heads, we could get 3 heads. Those are the different possibilities. And then what's the probability of it happening? Well, if you list off the number of different ways I can get it, you'll find that these are the probabilities. Because of the 8 different flips of the coin that I could have, of the 8 different series of flips, the only way to get no heads is to get all tails. Tails, tails, tails. So that's the one way that it can happen. If I want 1 head, then there are 3 different ways that can happen. I can either have the first flip be heads, the second flip be heads, or the third flip be heads. So there are 3 different ways out of the 8 possible series of coin flips that would give me 1 head. And then 2 heads, well, that would be 3 different ways as well. The other way you can look at it is if I have 2 heads, I would want 1 tail. So I could either have the first flip be tails, second flip be tails, or the third flip be tails. That's a combination, by the way. We talked about that. 3 choose 2 is 3. It's Pascal's triangle, 1, 3, 3, 1. 0 Pascal's triangle. And then the only way we can have 3 heads is if they're all heads, so only one way that can happen. But this is the idea of what this distribution looks like. Value on the top row, probability of it happening on the bottom. Right? So let's actually make one of these. Probability tables ourselves. It's going to look pretty similar, but it's not quite going to be the same. And just like in the last chapter, all of our probabilities of all the events put together should add up to 1. One eighth plus 3/8 plus 3/8 plus 1/8 was 1. So I'll give you a second to read the problem. We have international and domestic flights. And make sure you know the variable that we're keeping track of here. Make sure you know the variable that we're keeping track of. Usually on a question like this, it's easiest to do the ends. So try and do probability of 0 and probability of 3 first. Those are the easier ones to talk about. And then try and think about what needs to happen in order to have 1 and what needs to happen in order to have 2. And we're keeping track of the amount of domestic flights. So if we have 3 domestic flights, we need domestic, domestic, domestic. We need all 3 domestic. What's the probability of getting a domestic flight? 70%, or 0.7. So we have 0.7. That means we need the first one to be domestic and multiply. The second one needs to be domestic. And the third one needs to be domestic. So that's our probability distribution. 0.7 times 0.7 times 0.7. Or 0.7 cubed. I believe that should be 0.343. If I'm doing my mental math correctly. For 0, that means the opposite. I need all three to be international. International, international, international. So that means I need the first one to be international. And, multiply. I need the second one to be international. And I need the third one to be international. And I believe that should be 0.0027. Yeah. So less than 1% chance of that one. Now, the next one is trickier. If I want one domestic flight, I could have a domestic flight, then an international flight, and an international flight. I want one to be domestic. I want the other two to be international. So if I want one to be domestic, then I have 0.7 for the domestic, and the international, and the international. 0.7 times 0.3 times 0.3. Now, the thing to remember is just like with the coin flips, there are three different possibilities that could give me one domestic. Because I could also have international, domestic, international, and I could also have international, international, and domestic. So because there are three different ways that can happen, this is the probability of this specific combination of DII. So since I have three other possibilities, that triples my probability. I'm getting 0.189. Someone double check me on that one. Make sure my mental math is still working this morning. And then see if you can figure out what 2 is going to be. different ways it could happen. Seven. That means this one is 0.027. Okay, am I good now? Okay. So 2 of them being domestic and 1 of them international. There are 3 different ways that can happen. And take all these probabilities, add them together, and they should add up to 1. So our next question is, how many domestic flights should we expect to get requested? If I get 3 calls, and I'm keeping track of how many of them are domestic, we can ask, well, how many of them should we expect to get requested? And because it's asking a question of how many we expect, we're going to have a formula for this, and it's going to be called the expected value. So you might, a reasonable answer here might be, well, 2, because 2 is the most likely outcome. So most of the time we should expect 2, but not all of the time. And so basically what we're going to do is we're going to have a formula that's going to calculate basically the mean amount of flights that we would expect. And the way that we're going to do that is that, well, about 2% of the time we should expect none. And about 18% of the time we should expect 1. And so what we're going to do is we're going to use the values that we could get to weight how much we should factor it into the probability. So in other words, because the 34% of the time we're going to expect 3 of them, we're going to triple this value in our calculations. And we're going to combine this kind of weighted average in a formula called the expected value. So to find the mean or expected value, we're going to go across our row, and we're going to take whatever value is in this table times the probability of it happening. And then we're going to go on to the next column, and we're going to take the value times probability of it happening, plus the next value times probability of it happening. And then we're going to add all those together, and that's going to make up our mean. Like another way you could do this is to say that, like, since we expect this to happen 2% of the time, like if we had 100%, so per 100, if we had 100 of these things, we would expect about 3 of them to be 0. So you could write a list of 100 numbers, 3 of them be zeros, about 19 of them would be 1s, and then about 44 of them would be 2s, and about 34 of them would be 3s. So you'd have this big long list of a couple zeros, a few 1s, a whole bunch of 2s, and then a bunch of 3s. And you would add all those together. So we're just taking, since we'd have about 18 1s, 1 times 18 would be 18. And then dividing it by 100. Since we already have those proportions, that's kind of the idea of what we're doing here. So to show you how this formula looks in this table, expected value for x. We're going to take 0 times the probability of 0 plus 1 times probability of 1, which was 0.189, I think, plus 2 times probability of 2, plus 3 times probability of 3. We're just going to read across the table and do value times probability of it happening and add them together. Someone calculator for me. I've done my mental math for the day. We said that 2 is our most likely outcome, so hopefully our answer is somewhere around 2. What do we get? 2.1? So that is kind of our mean amount of flights that we would expect to be domestic. If we received a whole bunch of calls, on average, about 2.1 of them would be domestic. That's the idea here. So let's do one more of these for the day. So go ahead and read this problem, and I want you to try part A on your own, which is asking you to do an expected value for this table. So just make sure, one thing to make sure that you know is that just because this is a mean, and just because it's called expected value, doesn't mean it's the value that you expect. This does not mean that I'm expecting a commercial that's 46.5 seconds. In fact, none of the commercials are 46.5 seconds. That is not a choice. The choices are 15, 30, and 60. But it does say that on average, if we ran a whole bunch of these commercials, on average, in the long run, we would expect them to last 46.5 seconds on average. A collection of them. So, let's move on to part B now. We're going to make a new variable, y, being cost. And we're going to make a distribution with y. So we're going to make a new table here. That's what we're going to add to this problem. We have y, and we have the probability of y. There should still be 3 choices. So let me divide that better. So what are the choices for our variable y? What are the values that we could have here? We have 500, we have 800, and we have 1,000. 500, 800, and 1,000. And what is the probability of 500? 0.1, because it still hasn't changed from mean and 15-second spot. We still have 10% of the mean 15 seconds. So it's still 0.1. This is still 0.3. This is still 0.6. Those values haven't changed. But now that means that gives a slight tweak to the formula. So we need expected value for y. Value times probability of it happening. So the value this time, instead of 15, now we're at 500 times probability of 500 plus 800 times probability of 800 plus 1,000 times the probability of 1,000. The units here were seconds, so the units down here are going to be dollars. You have calculators. Work it out. 800 and what? 890? Again, we don't expect to spend $8.90 on a commercial. That's not a choice. We're expecting that on average, in the long run, if we looked at a lot of these commercials together, they would cost on average about $890. So remember that it is a mean. It is not literally a value that you expect. A lot of the time, it's not going to be a value that you can get at all. Mean is going to be a long-run average. Questions on that? I got a homework assignment for you. So that's the first homework assignment of this chapter. We should be able to finish the rest of these notes tomorrow. And then I'm going to jump on Wednesday to section 3 because I think it's a more important section. If I don't get to section 2 and I have to throw it out and cover it later, then I'll throw it out and cover it later. But section 1 and section 3 are the really important ones. The usual amount, so about 4 to 5. That also depends on